Hi, everyone, and welcome to online lecture 29, Simple Linear Regression, Part 2. So let's start off with a couple of review slides, okay? Let's start off by recalling that correlation and regression are very, very similar. They still have two continuous variables, still focused on relationships and associations, and they have very similar assumptions. And if you recall, correlation gives us the direction and strength of a relationship, but regression takes us one step further by allowing us to predict one variable from the other. So how does that work? First off, we label one variable as independent x and one variable as dependent y. Then we find a straight line through the data that provides the best fit for that data. That's called the best fit line or the regression line. Now remember, we're going to let SPSS do that process. And then we are given the equation for that line. That's what we can use to predict. Okay. So again, we call one variable independent x and the other variable dependent y. Find that straight line and find the equation for that line. And remember, correlation didn't label anything as independent and dependent. So now we're back to, like every other test we've talked about, having an independent and dependent variable. Okay. Now, the next thing I want to talk about is issues with simple linear regression. And we did talk about the first of these issues, which is that nonlinear relationships cannot be interpreted, right? So we have no tool in our bag of tools or toolbox that we can use to actually assess this kind of situation. So if you see this on an exam or what have you, just know there's nothing we can do with it. Okay. All right. Now, the next issue with simple linear regression is, again, very, very similar, or in fact, the same as what we had with correlation. It's restricted range. And if you remember, the way this one works is if you do not actually look at the whole range of x values of your independent variable, right? If we only look at NBA players when we're trying to look at height and basketball ability, right? If we restrict our sample and then try to generalize to a larger population, we run into this restricted range problem, which basically means we could not find a result when there really is one, or we could find a result when there really isn't one. Okay, so that's the issue with restricted range. The next issue I want to talk to you about is outliers. Outliers. So if you look at this, you see three kind of obvious outliers: McDonald's, Ford, and Pepsi. Now, the question is not just, is it an outlier, but does it make a difference? Is it somehow changing our regression line? So let's start off by looking at our regression line just like this. And we can see that the R squared is 0.066, not particularly large. Not a very strong relationship. Okay. So which outlier do you think is most influencing this relationship? Is it Pepsi? Is it Ford? Or is it McDonald's? So take your guess. And then what we're going to do is we're going to remove these one at a time and see what happens to our line. Okay, let's start. So I just removed Ford, and you can see the line didn't change very much. We went from 0.066 to 0.057. Not very impressive. Okay, so it's not Ford. Now I removed Pepsi. Line changed a little bit more, but again, not by much, 0.053 now. Now let's remove McDonald's. Wow, that's a big change. Suddenly the line shifts dramatically, and we went from 0.066 to 0.263, 26% of the variance, approximately. That's a huge change. That's important. Okay, so McDonald's, which was far away on both the X and the Y, sitting all the way down here, was really the most influential outlier. And what's the point of this exercise? It's to say that outliers can really influence our regression line too. So outliers can be really problematic. Not always, but sometimes they can be really problematic and really change what's going on. Okay. And we have one more issue with simple linear regression that we did not have with correlation. And this is called extrapolation. And the idea is that you shouldn't make predictions beyond the bounds of your data. So let's take an example. We're going to use age in months to predict height in inches in 2 to 15-year-olds. So we have our regression equation. It's y hat equals 0.1992x plus 30.3677. So a 5-year-old is predicted to be around 42.3 inches tall. That makes sense. A 15-year-old is predicted to be around 66.2 inches tall. Also believable. A 75-year-old is predicted to be around 209.6 inches or about 17.5 feet tall. Okay, so what went wrong here? Right, that's an awfully tall 75-year-old. I don't think that's really true. What went wrong is that a regression equation will assume that your line continues in the straight line. That's what a regression, simple linear regression is all about, right? That straight line. But what happens with height? At some point, height levels off for us, right? It levels off. So by going beyond the bounds of our data, which was just 2 to 15-year-olds, we made an error. Okay. So we don't want to extrapolate. We don't want to have outliers. We don't want to have a restricted range. And we can't deal with nonlinear relationships. Here's another example of extrapolation. So we have this woman who just got married. And yesterday she had 0 husbands. Today she has 1 husband. As you can see, by late next month, you'll have over 4 dozen husbands. Better get a bulk rate on a wedding cake. Cute. Okay. So we've been talking about simple linear regression for a while now. And we keep talking about using the line for prediction and those sort of things, right? We're talking about using the line for prediction. We're talking about problems of simple linear regression. But what we haven't talked about is how do we know if our regression is significant? How do we know if it actually matters? So that's where we get into an analysis of regression. Now, this is very, very similar to our ANOVA or analysis of variance. And it even uses an ANOVA table and an F ratio. So to understand this, we're going to work our way through an example, all the way through using SPSS to understand how this part works. So we're going to look at a study of helping behavior among friends. The researcher believes that increases in self-efficacy, which is a belief in one's ability to help, predicts increases in total help scores, both quantity and quality of help. Okay, So does self-efficacy predict total help scores? The alternative hypothesis, increases in self-efficacy, does predict increases in total help scores. The null, increases in self-efficacy, does not predict increases in total help scores. One-tailed or two-tailed? One-tailed. Sorry, I didn't have that there, but it is one-tailed because we're talking about increases and increases. We're talking about a direction. Had it said increases and decreases, it would still be one-tailed. It's just that we would expect our slope to be negative. Here we expect our slope to be positive, but if they went in opposite directions, we would expect our slope to be negative. Okay. So we start off with some basic information. Not particularly interesting. Interesting, I guess, that we have 537 people. That's a lot of people in this study. That's great. And then we start off here with a correlation. Okay. And it's a mighty strong correlation, 0.567. And our sig value is less than 0.001. Remember that rule? We always say p less than 0.001 whenever we see the 0.000. Okay. So very strong, very significant correlation between efficacy and helping. Okay. Now, this isn't really that helpful. It's just telling you what we're going to enter into the equation. It reminds us that our independent variable is that efficacy measure, and the dependent variable is our combined help measure. Okay, now we're finally getting into some interesting stuff. We have our R again, 0.567, our R squared, 0.321, and something we call an adjusted R squared, 0.320. And this is just adjusting for the fact that we are working with a sample, not a population. Okay, so it's just bringing it down just a little bit. Still a very nice number. Okay. Here's that ANOVA table I promised you. Right? Instead of between, we have regression. This is the good stuff. This is the stuff we like. Instead of within, we have residual. Or when you think of residual, you think of leftover, right? That's our error. And then total. We still have sums of squares, DFs, mean squares, and most importantly, F and our sig value. That's our P value. P less than 0.001 in this case. Okay. Now this P value is going to match something on the next page, and I'll show you in just a second. Okay, but we can conclude from this that our regression is significant. If our regression is significant, it's okay to use for prediction. If our regression isn't significant, we don't really want to use it for prediction. Okay, but this time it is, so let's move on. Here's what we get next. Now, this is the way that SPSS gives us the information for our regression equation. So let's tear it apart. Okay, so we've got, in this first column, we've got A for intercept, B for slope. So you can think it's alphabetical, right? A, B. This p-value over here by the slope will always match what's on the previous slide. Now I know in this case, this one happens to match too. That's purely coincidence. This is the one by the slope that will always match. So we have an A intercept, a B slope. Excuse me. We can fill in the B, the A into this equation. Whatever X we want to choose, then for self-efficacy, we can pop out whatever our y hat, predicted y, our help score would be. Okay. Here's a scatter plot with the line through it showing you how this looks. Again, remember that r squared was 0.321, or the adjusted was 0.320. And here's that regression equation written out nicely for us. And we can see this looks like a very nice relationship, very strong relationship. Okay. So now I'd like to look at one more example with you. And this one's going to be age. Let's see if a person's age predicts their help scores, how helpful they are. Same N, 537. Now we look at the correlation, 0.053. That's a lot lower than last time. And we can see it's not significant, 0.111. How do we know it's not significant? Because that number is higher than our alpha of 0.05. Okay. So we enter age into the model, right? We're entering age. Age is going to be our IV. Combined help is going to be our DV. Here's our information this time. Here's our R of 0.053, the R square of 0.003, 0.3% of the variance, and our adjusted R square of 0.001, 0.1% of the variance accounted for. Not looking good, guys. Here we go. Here's our ANOVA. Remember, regression, residual, total. We look at the F, and most importantly, we look at the sig value, 0.222. This time, it's not significant. This time, it's not less than 0.05. So really, we can stop here, right? It's not significant. We shouldn't use this equation for prediction. But here's the thing about SPSS. It's going to give us that equation anyway. It's going to give us that information no matter what. It's always going to give us a line. Because that's kind of what we asked for. So here's, just for purposes of looking at it, we'll look at it. Here's our A again. Here's our B. Here's that matching p-value of 0.222. Now, even though we have a line here, we don't want to use it for prediction. And I'll show you why. I'll show you how it looks. Like that. Looks like a mess, right? Here's our R squared of 0.003. Remember, it was adjusted R squared of 0.001. Here's a line. Drew a line through the data, but that's kind of a blob. That's kind of a mess here. And if we can't tell, if we're not a visual person and we don't see it that way, just look at the p-value. And I should say up here, look at the p-value. Okay. Now this is optional, this last piece right here. If you like TED Talks, maybe this is something to do over break or whenever, but this is a fun TED Talk about lies, damn lies, and statistics about TED Talks. I just share it with you because you might be interested in a different type of regression example. That's kind of fun. That's all I have for you for now. Take care, stay well, and I'll talk to you again soon.